What if your cells had their own armor to keep you healthy? They do. It's called the glycocalyx. This thin protective layer coats every blood vessel and cell in your body. It helps your circulation run smoothly, keeps nutrients flowing where they should, and protects against inflammation. A healthy glycocalyx means better blood flow, stronger barriers in your gut, and improved insulin sensitivity, all key to good metabolic health. But how can you support it? By keeping blood sugar stable, eating nutrient-rich foods, and staying active. When your glycocalyx is healthy, your whole body functions better. This is lecture 121 of the Metabolic Classroom. Looking to improve your own metabolic health? Visit insuliniq.com for courses, coaching, consultations, and a 10-day free community membership trial. To dive deep into the science behind metabolic health, become an insider at benbikman.com, where you'll enjoy my exclusive content, ad-free podcasts, live stream Q&A access, and more. Welcome to the Metabolic Classroom. I'm Professor Benjamin Bikman, a biomedical scientist and professor of cell biology. Today we're examining the glycocalyx, a critical yet often very overlooked component of cell structure, and because it affects cell structure, no surprise, it has an influence on cell function or cell biology. As you'll learn, it's involved in countless aspects of human physiology insofar as we are a sum of all of our cells and how they function. As we start the mini lecture, we'll begin with an overview of what the glycocalyx is, then discuss its locations throughout the body, or at least some of them, and its roles in regulating physiology and cell biology. Our focus will be on its functions in the gut epithelium, the vascular endothelium, and then I wanted to touch a little bit on the role of the glycocalyx in fat cells. And of course, no surprise, that has some metabolic connections as well throughout all of this. Now, I just chose those three sites, again, gut, blood vessels, and fat cells, out of interest, but there are more instances where the glycocalyx is relevant, so you just need to know that going in. I narrowed it down a bit just for the sake of a timely discussion and mini lecture. So to get things started, what is the glycocalyx? It is a carbohydrate-rich layer. Now, you might be making some assumptions. Don't make any assumptions yet when you hear me say the word carbohydrate. So it is a carbohydrate-rich layer that coats the surface of most cells in the body. It's composed primarily of a handful of molecules, including proteoglycans. You can hear the word gluco or carbohydrate, that word there, glycans, proteoglycans, glycoproteins, and even glycosaminoglycans. Yes, let me say that one more time. Glycosaminoglycans. A main one that actually becomes quite relevant in the fat cell is heparin sulfate. That's a glycosaminoglycan. And chondroitin sulfate. You might have heard of chondroitin. Some people take that as a supplement, and also hyaluronan. These are all coming together to form a gel-like structure. So it's like they're woven together along the surface of these cells. On endothelial cells in vivo, so within the living organism, the estimates of how thick this is range in the order of just a few tenths of micrometers. So that's where it is at its smallest. But in other instances, it can get down to the level of micrometers. So it's even, or several micrometers, so quite a bit larger. So there's quite a size difference in how thick this gel-like layer of the glycocalyx can be, depending on whether it's in the large arteries, like where it's a few micrometers, or again, down at the level of individual cells, where it is going to be a few tenths of micrometers. So quite a bit smaller. But it's going to be, like I've said, it's everywhere. Red blood cells have them. White blood cells, immune cells have them. And it's typically going to be always a very small layer. No surprise. Now, back to the word carbohydrate. When I say carbohydrate-rich, because that's how I described the glycocalyx, a carbohydrate-rich layer, I don't mean the carbs on your plate, or I don't mean the glucose in your blood that you're measuring with the glucose meter. Those are free sugars, and of course we burn them or store them. But the glycocalyx sugars are structural, and they are assembled inside the cell and then covalently bonded or attached to proteins and lipids in the cell membrane. Then they're presented, they're flipped out, if you will, on the surface of the cell like a shag carpet, like me when I don't shave my head very often. There's this little bristle of these of this mix of glycoproteins, and they form the glycocalyx. So you don't eat this layer, you don't put it on or you don't put it off, and a high carb meal doesn't suddenly thicken it because there's more glucose, even though glucose as a molecule is a part of this complex. The cell will build and remodel the glycocalyx through specific enzymes over much, much longer time scales than when you might see your blood glucose levels climbing or dropping. And it will do this in tune to various signals and various needs of the cell and the physiology of that specific tissue. Like the gut will need a certain amount of glycocalyx, the endothelium will need some, and so on. Now, yes, as I noted, some of the building blocks ultimately come from glucose, but it's intracellular. So it's only when the glucose is coming in is it used then to create the glycocalyx by need. But as I'll come back to, chronically high glucose, paradoxically, is more likely to damage the glycocalyx through oxidative stress and some non-enzymatic glycation. That's the advanced glycation end products. So it's more likely to damage the glycocalyx than it is to feed it or expand it. And as I said, I'll come back to that more. But the glycocalyx layer serves multiple functions. It can serve as a selective barrier to control molecular permeability, so what can get past it. It also can sense mechanical forces like shear stress. That, of course, is very relevant in the blood vessels in response to things like high blood pressure. And it will bind signaling molecules to influence how the cell will respond, may or may not respond to that particular signal, that molecule. In metabolic contexts, the glycocalyx modulates nutrient transport, so the movement of things into the cell. It also modulates inflammation and even some cell-to-cell communication, all of which is essential for processes like glucose uptake or the metabolism of fats coming into and then being metabolized within the cell. With all of this in mind, it's no surprise to know that disruptions to the glycocalyx, like shedding due to hyperglycemia or oxidative stress within the cell, can contribute to metabolic disorders, even including insulin resistance. The glycocalyx is present on the plasma or the cell membranes of virtually every single animal cell on the planet, including a bunch within our own bodies that we all care about, like neurons, muscle cells, red blood cells, white blood cells, fat cells, and more. On the erythrocytes, for example, the red blood cells, there is some a unique form of the glycocalyx. We have a very dense, what's called sialic acid-rich sugars that create a negative surface charge that actually helps limit the red blood cells from aggregating and binding together. So it's a way of ensuring that the red blood cells are not connecting too readily and becoming too sticky, lest we start to form blood clots. So the glycocalyx on a red blood cell helps the cells have a little bit of a repulsion against each other. Now, there are instances when the blood cells do start to clot together, but that's beside the point for now. In its normal unstimulated state, then the red blood cells are going to have a little bit of a mild repulsion to each other, in part thanks to the glycocalyx. Now, one part I haven't mentioned is the blood-brain barrier, but anytime you think of something that is lining a part of the body, including the blood-brain barrier, you can also think of the glycocalyx. It's, again, relevant in the blood-brain barrier. Also, the lining of the lungs. The alveolus rather, the alveoli are the little sacs, and the alveolar epithelium, or the lining of it, has its own glycocalyx. And interestingly, that lung glycocalyx interacts with surfactant. You might not have ever heard of surfactant if you haven't ever looked at lung physiology. But surfactant is this watery / oily substance that reduces the surface tension of the alveoli, which makes it easier for the lungs for us to breathe in and out. You also have the glycocalyx in the kidneys to protect filtration barriers and more. But today, as I noted earlier, I want to emphasize more on the gut, the blood vessels, and the fat cells because of the interesting metabolic regulation and, of course, because of my ongoing, permanent, seemingly interest in adipose tissue. Okay, so let's move on to part of what the glycocalyx is doing in cell biology. All of that previous ramble was meant to be more of an introduction. The glycocalyx influences physiology and cell biology by functioning as this selective filter for molecules based on size and charge. It also, as I noted, acts as a mechanosensor for fluid dynamics, in other words, analyzing shear stress, and also finally a scaffold for things like growth factors and adhesion molecules. And adhesion molecules are these hormones, if you will, or proteins that are part of that cytokine family, some of which can promote inflammation, others promoting an anti-inflammatory signal. For instance, the glycocalyx can trigger nitric oxide production in response to shear stress, thereby promoting vasodilation, the expansion of the blood vessels. And it can limit white blood cell adhesion to the walls of the endothelium. And that can, of course, reduce inflammation. That absolutely would have some relevance to atherogenesis. If you can block or reduce the degree to which white blood cells are binding to the walls of the blood vessels, then you're going to reduce the formation of atherosclerotic plaques. In metabolic terms, alterations to the glycocalyx are linked to conditions like endothelial dysfunction, namely atherogenesis, as well as some impaired nutrient handling. All right, let's get into the endothelium. In the vascular or the blood vessel endothelium, which lines all of the blood vessels, so think of the wall of the blood vessel, the glycocalyx forms a prominent layer that extends into the bloodstream. So it's pointing in. And the thicknesses can be up to several micrometers to whatever degree you might care about that. In the large arteries, and then a few tenths of a micrometer in the smallest of the blood vessels, namely the capillaries. It responds to hemodynamic forces, so the pressures in the blood vessels, by activating pathways that release nitric oxide, helping to maintain vascular tone or caliber or size, and thereby preventing or helping prevent hypertension. The glycocalyx also restricts permeability to plasma proteins. So in other words, making sure that proteins like albumin stay in the blood rather than leaking out of the blood vessel. By doing that, it helps prevent edema. Edema is that uncomfortable phenomenon of when you'll have a limb, for example, start to swell because you're retaining too much water. That's actually a function of water leaving the blood vessels and accumulating in the space outside the blood vessel. Well, the glycocalyx helps keep those proteins in. And if the proteins are staying in the blood, the water is going to be more likely to stay in the blood. And then finally, the glycocalyx also creates a lubrication layer for efficient blood flow by repelling the erythrocytes through the net. So again, it's helping make sure that the red blood cells are just staying in the blood and moving well, not aggregating or clumping together. But of course, no surprise, if the glycocalyx starts to experience some degradation, which, as I noted, can be triggered by oxidative stress, it can be triggered by disturbed blood flow in certain areas, but also metabolic factors like hyperglycemia and consequences of hyperglycemia, namely the formation of advanced glycation end products or AGEs, all of which not only can compromise the glycocalyx, but interestingly play a role in atherogenesis, the most famous of all blood vessel problems. Acute hyperglycemia, for instance, has been shown in healthy adults to reduce the systemic endothelial glycocalyx volume by roughly half. So you take the glycocalyx of a healthy individual, induce hyperglycemia, and it will have shrunk by about half. So that can then lead to a state that is more likely to promote coagulation of the red blood vessels, as well as infiltration of white blood cells or immune cells into the walls of the endothelium. Now, I alluded to this earlier, but you might be wondering how blood glucose fits into this picture. Inside the endothelial cells, when the endothelial cells take in glucose, that glucose will get converted into what's called nucleotide sugar donors. These are molecules like, this is going to sound funny, UDP glucnac, and I'm saying that in a way that it's not totally spelled. If you wanted to look into this a little more, just type in UDP-GLC-NAC, as well as UDP glucuronic acid. That enzymes will use those molecules to build the structure of the glycocalyx. So in that sense, glucose can provide some of the bricks. But again, it is when there's glucose in the endothelial cell, and then it diverts the glucose into that particular pathway, building those molecules that become the structure of the glycocalyx. But when glucose is high in the blood, so when it's really high in the plasma, the outside environment, outside the endothelial cell that is, sends a very different message. You have potential for more oxidative stress, and you absolutely have a greater formation of advanced glycation end products, which will bind the receptor for advanced glycation end products, or RAGE, R-A-G-E. And when RAGE signaling is up, it activates these enzymes that will break down the glycocalyx, like heparinases, hyaluronidases, metalloproteinases, and it will in turn also blunt the production of nitric oxide. So it's almost as if the brick factory that's running inside the endothelium, but there's a demolition crew that's on the outside, which is chipping away at the glycocalyx. So while the one molecule, the glucose, is providing the structure for the brick factory to make the bricks, the glucose that's outside the cell is acting like, as I said, this demolition crew, and it's damaging the brick wall that the brick factory is trying to build. Hopefully that metaphor is not getting lost or too complicated. But remember, in the endothelium, that means that as the glycocalyx starts to thin, the endothelium becomes more permeable. So it's much more likely that you might have the invasion of lipoproteins, you might have the invasion of white blood cells, thereby increasing the risk potentially of atherogenesis. Meanwhile, back to the advanced glycation end products, they're going to be activating immune and pro-inflammatory signals anywhere else throughout the body. But from a cell biology perspective, we need the glycocalyx to regulate or modulate the interactions between endothelial cells and the circulating immune cells, dampening the pro-inflammatory responses. So when we have metabolic conditions like obesity, some researchers hypothesize that an adapted endothelial glycocalyx in the adipose tissue vasculature, not just the fat cells itself, but in the blood vessels of the fat cells, it actually may help prevent too much inflammation. So again, when the glycocalyx is working well, but of course, as the glycocalyx is degraded, that's going to exacerbate the consequences. All right, now let's move from blood vessel to gut, because when you think about the glycocalyx playing the role of filter or keeping some things out, allowing some things in, of course, the intestine becomes very relevant here. In the intestinal epithelium, or the lining, the glycocalyx will coat the microvilli of the enterocytes. Now, the microvilli are, if you're watching, or I'll try to explain this too, it's like these finger-like little projections. So if you were to zoom in at a microscopic level of the cells that line the gut, you would see these little columns of structure popping up and down, weaving up and down, like the fingers on a hand. And that is to enhance the surface area of the gut epithelium, to then enhance the absorption of molecules, just to make sure that we're getting everything in that we want. But it needs to be a little porous. We need to allow some things through. Of course, a large part of that is there's the mucus layer, but then of course we have the glycocalyx. And the structure will selectively permit nutrient absorption, ideally, while excluding pathogens and toxins. So that's going to help maintain the gut's primary role of only allowing in what we want in. There is some fascinating dietary relevance here. For example, certain human milk oligosaccharides, such as the fucosyl lactose molecules, there are a couple of them that are relevant here. So milk has these fucosyl lactose molecules that have been shown at least in vitro or in cell cultures, to enhance the signals of a key part of the glycocalyx, the heparan sulfate part, and the hyaluronic acid. This helps stabilize the epithelial glycocalyx, which can support barrier maturation in early life. So this is one of the reasons why the breastfed baby may have an advantage in just overall health, because mother's milk is providing some of these molecules to enhance the formation of a robust glycocalyx. There are also some hormone signals that are introduced during weaning that can upregulate some and help mature some of the molecules of the glycocalyx, further supporting healthy epithelial function and thus healthy immunity too. In pathological or harmful states, we will often have increased intestinal permeability. This is often colloquial referred to as leaky gut, and that's a fine term, although the conventional medical community might not like it. It is an accurate term, but we just have too many things slipping through the gut when we don't want it. Now, there can be certain stressors that accelerate this. Polyunsaturated fats have been shown to increase permeability. Alcohol or dysbiosis, in other words, an altered, unhealthy microbiome, can lead to thinning the layers of the glycocalyx and even enhancing or accelerating its degradation. When that is dysfunctional, you can start to have bacterial endotoxins. One that I've spoken about in previous metabolic classrooms before, LPS or lipopolysaccharides, is a big one. You can also have various antigens that are now translocating across the epithelium, getting into the blood, whereas the glycocalyx would have normally been woven together like a barbed wire fence to keep those things out, or acting more like a checkpoint, allowing some things in. As these molecules are now slipping in, you start to get systemic inflammation and what's sometimes referred to as metabolic endotoxemia. The glycocalyx, of course, working in tandem with the overlaying mucus layer, forms a very important size exclusion barrier. In other words, it will only allow certain molecules that are of a small enough size to get through. But the erosion correlates with conditions like inflammatory bowel disease, where we have too much bacterial penetration, harming the epithelium. Now, there are some emerging therapies in this regard, such as probiotics meant to boost the production of not only ideal mucus levels, but also support the glycocalyx in restoring its structure. And these are, in fact, currently being explored to help mitigate some of the consequences of a weakened glycocalyx and the subsequent increased intestinal permeability. Now let's move from blood vessels past the gut and get into the fat cells, one of my favorite tissues in the human body to study. In fat tissue, the cell's sugar coating, or the glycocalyx, acts like a bit of a control panel, interestingly, that helps decide when a precursor cell will commit to becoming a mature fat cell and how that cell will handle fuel. Think of it as a finely patterned layer that will catch and organize some of the growth cues at the surface of the fat cell. When this pattern is healthy, then precursor fat cells, so pre-adipocytes, will know that it's time to mature in an orderly way into a functional adipocyte. When it's disturbed, the cells will not mature. They will stay as immature pre-adipocytes. Remember, lest you think that's an advantage, fewer fat cells is not an ideal way for the human body to store fat. Because then the potential then is, if there is a pressure to store fat because of an insulin signal being sufficiently high combined with sufficient energy or calories, you don't want to store fat in fewer but larger fat cells. That's that phenomenon of adipocyte hypertrophy. And again, a weakened glycocalyx is compromising the body's ability to make fat cells. Don't think that's a good thing. There's a neighborhood effect here too within these microenvironments. In high glucose states, enzymes can clip pieces off of the adipocyte glycocalyx, and that then starts to spread the problem. These molecules that have been snipped off can aggravate nearby capillary cells, or the capillaries through the fat tissue. It will aggravate the endothelial cells or the glycocalyx of those endothelial cells of the capillary, which can then increase inflammation and further restrict blood flow. Remember from previous lectures, as fat cells are undergoing hypertrophy, which a compromised glycocalyx is forcing, one of the consequences of this is that the hypertrophic adipocytes become hypoxic. They cannot get sufficient blood flow and thus sufficient oxygen. They begin to release their own pro-inflammatory proteins in order to try to stimulate new blood flow. But now we're actually adding to this even further, because if the hyperglycemia is resulting in some shedding or clipping of sections of the glycocalyx from the adipose tissue, it's further promoting inflammation. Now, that might help correct the blood flow to the fat cell, but it does have systemic consequences. If you start increasing inflammation throughout the body, you are not only enhancing your risk of atherosclerosis, but you are most certainly driving insulin resistance, because after all, inflammation is one of the cardinal causes. So protecting that glycocalyx layer of the fat cell ensures healthier fat cell turnover. So when a fat cell dies, which it does, fat cells are not immortal, you help ensure that it has a premature version ready to maturate and come in and fill that metabolic gap. All right, let's wrap it up. In summary, I hope you appreciate this now. The glycocalyx is a very important regulator of permeability, also of mechanotransduction. That's the idea of sensing the shear stress, and even signaling in the endothelium, the gut epithelium, and the adipocytes, with very relevant implications for cardiometabolic health. The roles of the glycocalyx, from filtering nutrients in the gut to helping sense growth signals in fat cells, underscores the importance in preventing dysfunction in disorders like diabetes and even inflammatory states. We want to protect our glycocalyx. As I've noted a few times in this mini lecture, one way to do that is to avoid these frequent hyperglycemic bouts. So the more a person is consuming refined sugars and starches, the more they are spiking their blood glucose, albeit acutely. That has been shown to be sufficient to reduce the glycocalyx. Remember, some human evidence, some correlates of it in humans suggest that you can shrink that glycocalyx by about half. So let's keep our blood glucose in control to help that glycocalyx do its job. Thanks for tuning into the Metabolic Classroom. If you found the episode informative, I hope you did, please leave a review and consider subscribing. Until next time, more knowledge, better health. Looking to improve your own metabolic health? Visit insuliniq.com for courses, coaching, consultations, and a 10-day free community membership trial. To dive deep into the science behind metabolic health, become an insider at benbikman.com, where you'll enjoy my exclusive content, ad-free podcasts, live stream Q&A access, and more.